Origin of the Star's Chemical Elements and Stellar Formation by Carson Bolt and Ben Huard. Tiny variations in temperature and density allow matter to clump together to form giant gas clouds of helium and hydrogen. As these clouds grow, they begin to create spheres of gas which have increased density and pressure. Once the temperature reaches a certain level, the hydrogen begins to fuse into helium, forming a protostar. Fusion is the process of evolution of atoms when subjected to tremendous pressure and energy. While at lower energy levels, like charges can maneuver away from each other, there is a point when particles are moving so quickly that they are smashed together, forming a new element. However, the same process which births and sustains the stars also kills them. For when it can no longer reach high enough energy levels to produce super heavy elements, the core collapses and, depending on mass, results in several different star remnants. For 90% of a high-mass star's lifetime, it is engulfed in an equilibrium between gravity and nuclear fire. With an abundance of hydrogen within its core, the star will burn for millions of years. However, the intense gravitational pressure of the high-mass star makes each nuclear reaction more explosive, causing it to fuse more hydrogen into helium, making a high-mass star's lifetime shorter. When these massive stars exhaust their supply of hydrogen, its average density and mass increases. It begins to fuse helium together to form carbon, carbon into neon, neon into oxygen, oxygen into silicon, and then silicon into iron. Iron cannot generate enough energy to fuse into heavier elements. The fusion process stops, allowing the initial gravitational collapse to resume, causing the interior of the star to collapse, causing a supernova. It literally inverts its layers, having an interior acceleration near the speed of light. The amount of energy is so intense in a supernova that it reacts, creating every element in the periodic table. After this exotic reaction, two things can happen. The core of a smaller high-mass star will continue collapsing until the overcrowded neutrons within the star stop the collapse, forming a neutron star. If it has a bigger high-mass star, it will continue collapsing until the gravity is so intense that even light cannot escape it. This is called a black hole. In some cases, the angular momentum of a neutron star will result in a beam of radiation seen from Earth as a pulse, resulting in the formation of a pulsar. The interior collapse of a high-mass star releases enough energy to create every element on the periodic table. Every substance the star is made of fuses into heavier and more complex elements. Everything that the Earth, the solar system, and all life is made out of was created in the process of a supernova. Without these phenomena, the universe would be reduced to a cold mist of hydrogen with trace amounts of helium and lithium. In low-mass stars, the gravity is much lower, and so each nuclear reaction is under less external pressure. Low-mass stars will live for billions and more years than high-mass stars. An average low-mass star like our Sun has 7 layers, starting with the solar corona, upper chromosphere, lower chromosphere, the photosphere, the convective zone, the radiative zone, and finally the core. The thickness and density of the 2 layers surrounding the core slows down the speed at which light can escape the sun by forcing it to travel in many random directions. In fact, the light at which we see now is most likely created by nuclear reactions in our sun's core during the Ice Age. As the star begins to burn helium into carbon, it increases the core density and temperature, causing the sun's outer layers to expand. Slowly it burns heavier and heavier elements, heating up and further expanding until eventually it can no longer produce more heavy elements. When the core no longer fuses elements, it sheds its outer layers into space, revealing the cold, dead core of a star. By the end of the process, the star will be approximately the size of Earth. However, a theoretical prospect awaits, for scientists predict that the white dwarf can cool, becoming a black dwarf.